Welcome back, students. In this lecture, we'll discuss some analysis problems related to the topic strain energy due to axial loading. Okay. So before we move on to the actual problems, let's have a quick recap on what we already discussed in the previous lecture. Right. So in the previous lecture, we have seen what is strain energy and how to find out the instantaneous or maximum stress and expression for calculating the strain energy due to different kinds of axial loading. Okay. So first of all, we are seeing for gradual loading, the maximum stress is equal to sigma is equal to P by A. Okay, and the expression for strain energy U is equal to sigma square by 2E multiplied by V, which is volume. Right, this was nothing but the area under the load, resistance deformation curve. Right, it was the area of a triangle. Right, this was R and this was deformation delta. Right, then we are seeing for sudden loading, let us notice that the maximum instantaneous stress was 2 times P by A, where P is the applied force and A is the area cross section, and the expression for U remains the same. Then we are seeing for impact loading, okay, wherein the impact is caused by a falling object from a height of h. Right, so in such cases sigma is equal to P by A plus square root of 2 EPH by AL plus P square by A square. Here also the expression for strain energy remains the same. Okay, sometimes it can be noted that the deflection caused by the impact is very much less than the falling height, which means that h is very much higher than the delta L. In such cases we can neglect the deformation, and the expression for sigma can be calculated as sigma is equal to 2 EPH by AL whole raised to 1 by 2. Right, and the expression for U remains the same here also. Okay, then we are seeing for shock loading. So shock loading means due to any kind of shock there was an energy transferred, let's say it is capital U. Okay, in such cases also the bar will undergo some deformation of delta L, and which results in some stress and strain energy developed in the bar. Right, in such cases stress developed in the bar due to shocking loading is equal to square root of 2 UE by AL. Okay, wherein this U is the energy done by the shock. Okay, this expression is analogous to the previous expression. Here instead of U we have P into H, because P into H is nothing but the potential energy of the falling object. Right, simple. Here also the expression for U remains the same, which is strain energy. Please note strain energy is denoted by small u. Okay, so U is equal to sigma square by 2E multiplied by volume. Okay, then we have discussed about axial force which is varying along the length. Okay, which varies, which is P of X. P of X means the axial force value P varies along with the value of X. Right, in such cases we will have to go for the integration analysis. Okay, so U axial is given by this particular expression, half of integral 0 to L Px square by EA, okay, dx. This Px is again epsilon x multiplied by EA. Okay, so we can rewrite the expression as something like this also. Okay, that is not quite important as of now, we will have discussion later about this. Okay, another important case is wherein there is multiple members or multiple sections in the same member, or multiple materials in the same member, such as composite bars. Okay, wherein there is different materials in the same bar, or some bars wherein there is change in cross section also. In such cases what we have to do is we have to individually find out the strain energy developed in each of the sections, which is nothing but sigma square by 2e multiplied by an, and then we have to add up all the strain energy, each of the strain energies developed in each of the sections using the summation, right? Again, sigma is nothing but p by a if it is gradual loading, so you can substitute sigma as p by a and you will get this expression also. Fine. Let's get into the first problem. So here we have, let's read the question. A bar 100 centimeter length is subjected to an axial pull such that the maximum stress is 150 meganewton per meter square. Its area of cross section is 2 centimeter square over a length of 95 centimeter, and at the middle of the 5 centimeter it is 1 centimeter square. Modulus of velocity is given. We have to calculate the strain energy. Okay, so this is the expression. So total length is 100. In between there is a 5 centimeter which is having an area cross section of 1 centimeter square only. So we will consider this much portion as section 1. Okay, and remaining portion is having area cross section of 2 centimeter square, and the combined length of this and this sections are 100 minus 5, which is 95. Okay, so another thing given is that the maximum stress can be only 150 meganewton per meter square. We know that 1 centimeter is a thinner section than this, which means that the maximum stress is supposed to occur in section 1, which is the thinner section. Okay, so but in both the sections the applied force P is same. Okay, so in such cases we can find out what will be the stress in the section 2 also, what is sigma 2 also, by using this expression, right? So sigma 1 multiplied by a1, where sigma 1 is already given as 150, multiplied by a1 is 1 centimeter square, so we substitute that 1 centimeter square in meter square. Then sigma 2 is unknown, what is stress in bigger section is unknown, multiplied by area of the bigger section, which is 2 into 2 centimeter square, which is 2 into 10 raised to minus 4 meter square. So we get sigma 2 as 150 by 2 equal to 75 meganewton per meter square. The next step is we have to sum up the strain energy in section 1 and section 2 together. You see the expression sigma square by 2e multiplied by v, which is area into length. Volume is nothing but area multiplied by length, right? So we will use this particular expression. We know what is sigma 1, we know what is area 1, we know what is length of first section, divided by e. Everything is known. Only thing is you have to keep the units consistent. So herein we have used Newton and meter as the consistent units, and converted all the values into newtons and meters as base units. Okay, so we substitute all the values here, and finally we get what is the value of strain energy. U is equal to 2.953 Newton meters. Now let's see another problem. You can take a pause and read the questions here. Okay, so here the question is you have to compare the stress in the free end of the bars in each of the cases. We have two cases here. Okay, under the condition that the energy delivered is same in both the cases. So we have two cases, 1 and 2. In the first case we have a uniform cross section of A throughout the length L, and in the second case we have a two sections. Okay, one section of area A for a length of L by 4 from the free end, and then remaining section of area 2A for a length of 3 by 4 L up to the fixed end. Okay, a force will be applied at the free end. Okay, so when the force is applied, we know that stresses will be developed in the sections, each of the sections, right? So in the first case we can see that this is a uniform cross section, which means that stress will be uniform throughout. Okay, so let's call it as sigma 1. Okay, in the second case we can notice that there is a change in section, which means that in each of these two different sections the stresses developed will be different. Okay, we have a slightly higher stress developed in the thinner section than the stress developed in the thicker section, right? So let's say that the stress developed in the thinner section of area A is sigma 2, which is again the stress in the free end, and the stress developed in the thicker section is sigma 3. Okay, so if you compare for the case 2, the axial force is same in both the sections, which means that the sigma 3 and sigma 2 can be relation between sigma 3 and sigma 2 can be found out by telling that force is same in both the case, which means that sigma 2 multiplied by A is equal to sigma 3 multiplied by 2A, which means that sigma 3 is nothing but sigma 2 by 2. Now let's see what was the condition given. Condition is that the strain energy stored is same in both the case 1 and same case 2, and we have to find a relationship between sigma 1 and sigma 2. Okay, simple question. So we know what is the expression for U or strain energy. It is sigma square by 2E multiplied by volume. Okay, so for U1, sigma square is sigma 1 square multiplied by A, volume is A multiplied by L, right? So A multiplied by L divided by 2E. Okay, which is same as for the section case 2. We have two sections, so we have to sum up the strain energy in each of the section. So for the first section, which is of area A, we have sigma 2 square multiplied by area into length is L by 4. So we did that, area multiplied by L by 4 divided by 2A, plus for the remaining section the stress was sigma 3 and area is 2A and length is 3L by 4. So sigma 3 square multiplied by 2A, which is area, divided by multiplied by 3L by 4, which is length. Again this is 2A, but again we see that sigma 3 is nothing but sigma 2 by 2. So instead of sigma 3 we substituted sigma 2. Now we have an equation between sigma 1 and sigma 2, so we can solve and find out what is the relationship between sigma 2 and sigma 1, which is sigma 2 is equal to 1.265 sigma 1. Fine. Now let's see another problem. Okay, so read the questions thoroughly. So first of all, you can see that the applied force P is 50 kilonewton and it is suddenly applied to a steel bar. Length is 2 meter and area is 100. So you can pick up all these things and write it here. Okay, and the modulus of velocity is 200 kilonewton per millimeter square. So first of all, you can decide what is the base units you want. So I'll prefer here millimeter and newton, so I'll convert all the values into millimeter and newtons. Okay, so 50 kilonewton will be 50,000 newton, right? Area is given in millimeters, I is given, length is given in meters, 2 meters, so it is 200 millimeter. E is given in 200 kilonewton per meter square, which is 210 newton per millimeter square, right? So the first question is you have to find out the maximum instantaneous stress, which is nothing but sigma. In case of suddenly applied force, sigma is equal to 2 E. So sigma is equal to 2 P by E. P is already known, area is already known, so we can get sigma is equal to 100 newton per millimeter square. So leave that aside. The second question was to find out what is the maximum instantaneous extension. So we have to find out delta, right? So first thing is, if we know stress and we have already know modulus of velocity, which means that you can find out what is strain. Okay, E is equal to sigma stress by strain, sigma by epsilon, which means that epsilon equal to sigma by E. Okay, so we can substitute that and get what is strain epsilon. Once you have this value of strain, strain is nothing but change in length divided by original length, right? So from this we will know what is original length and what is strain. Only thing is we have to calculate delta L. So delta L can be calculated by multiplying strain with the original length. So the answer of delta L is 1 meter. Okay. The next thing is we have to calculate strain energy. So we already know this equation for strain energy. Sigma square by 2E multiplied by volume. Sigma is already known, which is 100 Newton per millimeter square. Substitute that. E should be substituted in Newton per millimeter square. Substitute that. And volume should be substituted in Newton and volume should be substituted in millimeter cube. So volume is nothing but area into length, right? So area is 100 millimeter. Sorry, yeah, area is 1000 millimeter and length is 2 meter, which is 200 millimeter, 2000 millimeter. Okay, so we get U as 50,000 Newton millimeter. Next step is you have to find out what is modulus of resilience. Modulus of resilience is nothing but proof stress per unit volume, right? So this equation for volume is not required. Um is equal to sigma square by 2E. We get the value as 0.0255 Newton meter millimeter per millimeter cube. This per millimeter cube is nothing but per volume it is. Fine. Now let's see one problem. So herein, read the question thoroughly. A 1500 millimeter long wire of 25 millimeter square cross section is hanged vertically. It receives a sliding column of 100 Newton weight and stopper at the bottom end. The column is allowed to fall on a stopper through 200 millimeter height. Determine the instantaneous stress induced in the wire and corresponding elongation. Determine the strain energy stored in the wire also. Take modulus of velocity of wire as 200 gigapascal. Okay, so first of all we have a wire of area 25 millimeter square. Its total length is 1500 millimeter. Okay, that's already given here. In between we have a weight which can slide by a height of 200 millimeter and fall on the stopper. Okay, so when it falls, it causes an instantaneous loading on the wire, right? So the height of fall is given as h is given as 200 and the load is given as weight of the load is nothing but the weight of the falling object, which is P is equal to 100 Newton. Okay, so we are asked to find out the instantaneous stress first, then corresponding elongation delta L, and finally the strain energy stored. Okay, so you can convert all the given data into newtons and millimeter square, millimeter as base units, and substitute that here. Okay, so the first, what is sigma or instantaneous stress, which is nothing but P by A plus P square by A square plus 2EPH divided by AL under the square root. Okay, so P is already given, which is the weight of the falling object, so 100 newtons divided by area. Again, this H is nothing but height of the falling object, area will be area of the wire, and L is the total length of the wire. Okay, all the details are known, so you can substitute and find that sigma is 465.89 Newton per millimeter square. So instantaneous stress developed due to falling of the object is 465.89 Newton per millimeter square. Okay, so once we have delta, sorry, sigma, you can also calculate delta, because you can, that is basic calculation. Delta will be strain multiplied by total length, right? What is strain? Stress by modulus of velocity. So instantaneous stress is 465 divided by modulus of velocity 200 210 to 3 Newton per millimeter square multiplied by original length, which is 1500. So you get elongation of 3.49 millimeters in the Y. And finally, to calculate U, you have the same old expression, sigma square by 2 multiplied by volume. Right? So sigma is already known, 465.89 divided by 2E multiplied by volume is volume of the wire, which is area is 25 millimeter square and the length is 1500 millimeter. Okay, so substituting, we'll get what is the value of u also, it is 20,348.76. Okay, the same expression alternatively you can see that delta is only 3.49, which is compared to the height of fault h is 200 millimeters. So 3.49 compared to 200 millimeters is somewhat less. So if you calculate sigma using the expression, sigma is equal to square root of 2 EPH by AN only, you'll get the value of around 461. Okay, so we can see that this is somewhere near to the value already calculated here. Okay, so we are not doing that, but for understanding purpose I'm just doing that. Okay, so that's it. We'll see more topics in the coming lectures. Thank you.